Hey everyone! In this video, we're going to learn how to solve basic trigonometric functions, a common topic in Calculus 1. These show up all the time in integration, limits, and applications, so let's make sure you're solid on them. So first of all, we need to know what a trig equation is. So what it is it is an equation where a trigonometric function is set equal to a numerical value. So let's say that we're given a trig function, such as sine of x. That could be set to a numerical value like 1/2. And for cosine, we could be given a numerical value such as -√3/2. And for tangent, we could be given a numerical value such as 1. So in all of these, we can see that we have a trig function and we have a numerical value that is set equal to that function. When solving trigonometric functions, the unit circle can be a helpful tool. So let's review that, and I'll teach you some of my methods that I use to memorize the unit circle. So we can jump immediately into the first quadrant, where we know the starting point is 0. The first radian would be pi/6, the second would be pi/4, and the third would be pi/3. Now, for the second, third, and fourth quadrant, I like to remember the radians as something like a phone number, which I'll write over here. So the numbers to remember are 2, 3, 5, 7, 5, 4, and 5, 7, 11. And you'll see where the numbers play into the unit circle in a second when I write everything out. So in the second quadrant, I can see that the number 2 goes here, and we know that the pi goes here. So 2, 3, 5, 7, 5, 4, and 5, 7, 11. And now you may be wondering how to get the values for the denominator. And the pattern that I see is that you can use the last quadrant's denominators and mirror it onto the quadrant that you're on right now. So for quadrant 2, we can use the last radian from quadrant 1 and mirror the 3 from down below onto the other one. So if we keep mirroring, we get 4 on the bottom, 6 over here. And if we now mirror the second quadrant onto the third, we can get the denominator 6, 4, and 3. And likewise, when we do the same thing, we get 3, 4, and 6. And then now, we need to fill in, the tops and the sides. And we know that this can be ended as 2 pi. We know that this over here is pi, which is 180. So when you're at 90 degrees, it's half of 180. So you could do pi over 2. And 270 would actually be 3 pi over 2. So now that we have all the radians for the unit circle, let's focus on the coordinates. So for here, we know that the coordinates is √3/2, 1/2. And at pi/4, the coordinates are √2/2, √2/2. And for pi/3, the coordinates are 1/2, √3/2. And like the denominators in the radians, these also mirror over to the next quadrant. So at 2 pi/3, the coordinate would become 1/2 √3/2, just like over here, mirrored onto that. And now the important thing to remember is the negatives and positives. So we can kind of visualize that by imagining this and this as the x and the y-axis. So now we know where negative x is, which is over here, and we also know where negative y is. So when we do that, we know that the coordinates inside of the second quadrant will be negative, positive. The coordinates inside of the third quadrant will be negative, negative. And finally, in the fourth quadrant, it will be positive, negative. So if we go back to this, the 1/2 over here would become a negative. And at 5 pi over 6, it would be negative square root 2 over 2, square root 2 over 2. And, oh, excuse me, this would be at 3 pi over 4. And at 5 pi over 6, it would be negative square root 3 over 2, 1/2. And over here, we mirror this coordinate onto this, and we can get negative square root 3 over 2, negative 1/2. And right here would be negative square root 2 over 2, negative square root 2 over 2. And right here would be negative 1/2, negative square root 3 over 2. And then once again, we finally mirror again to get 1/2 square root 3 over 2, square root 2 over 2, excuse me, negative square root 2 over 2, and square root 3 over 2, negative 1/2. And that mirrors back over to the first coordinate. And now we need to fill in tops and the sides again. So if we envision this as a circle with the radius of 1, we can see that the coordinate extending out in the positive x direction would be 1, 0. Towards the y would be 1, 0, or 0, 1. And then in the negative x direction, it would be negative 1, 0. And towards the negative y direction, it would be 0, negative 1. And now we need to know the correlation between trigonometric functions and the unit circle. And for this, it's important to realize these three things, where the cosine value is equal to x, the sine value is equal to y, and the tangent value is equal to y over x, or sine over cosine. Now let's work on some examples. So, in problem 1, we're asked to solve sine of x equals 1/2, given the boundary between 0 and 2 pi. So from this boundary, we know that we start at 0 and we go all the way around the circle back to 2 pi. So it's only one revolution around the unit circle. And so we have to ask, where is sine equal to 1/2 on the unit circle? And from the coordinates that we just went over, we know that sine is equal to 1/2 in these 4 places, but the value of sine here is positive. So we can ignore all the negative parts of the unit circle and only focus on the positive parts. And the coordinate right here would be pi over 6, and the coordinate over here would be 5 pi over 6. So we know that the solution is x is equal to pi over 6 and 5 pi over 6. Now, for our second problem, we're asked to solve cosine of x equals negative 1/2. And this time, we're not given restraints. This means that the answer can be a radian that's circled around the unit circle an infinite amount of times. So we need to remember to add plus 2 pi n at the end of our answer, where n represents the number of times circled around the unit circle. And now when we ask ourselves, when is cosine equal to negative 1/2, we realize that the cosine value has to be negative. So we can delete everything where the cosine value is positive and look at the left side of the unit circle. And we see that cosine is negative 1/2 when we're at the radians 2 pi over 3 and also 4 pi over 3. So the two answers would be 2 pi over 3 plus 2 pi n and also 4 pi over 3 plus 2 pi n. Now for problem number 3, we're given 2 sine of x minus 1 equals 0. And to solve this, we need to first isolate the trig function. So we can move the negative 1 and the 2 to the right side of the function. One, and then divided by 2. So this. And this is the same equation that we're given in problem 1. So we're going to have the same answer as well. But we also need to understand that we have no restraints in this problem as well. So the answers would be pi over 6 plus 2 pi n and also 5 pi over 6 plus 2 pi n. In problem number 4, we're asked to solve tangent of x equals 1. And for this problem, we want angles where tangent of x is equal to sine of x over cosine of x. And we get 1 when the value of sine and cosine are equal to each other. And if we look at the unit circle, the only place where sine and cosine are equal to 1 is equal to each other is at pi over 4. So the answer to this problem would be pi over 4 plus 2 pi n, as we're not given any restrictions again. Now, let's also look at some common mistakes when solving trigonometric functions. One of the common mistakes is forgetting the plus pi n. And by forgetting this, you miss all of the repeated solutions. And the second big mistake is forgetting the plus and minus, which makes you miss half of the answer. And lastly, it's knowing whether to use degrees and radians. And in Calc 1, you always use radians. So, in all, to solve trig equations, we first isolate the trig function, find all angles where it works, and remember to include the general solution if needed. I like to practice a lot, and by doing this it starts to click, so hopefully it does the same for you. If this helped, please like and subscribe, and leave a comment if you have questions.